just been hearing. Can everybody hear me clearly? X, queso, InMap, most recently Ring. These are examples of operating system tests, methods to detect what operating system is running on a computer over the internet or on the same LAN from another computer by testing how it looks at the network. Now that can mean looking at its TCP/IP stack or its ICMP implementation, or maybe its services or its services pattern. There's lots of ways to do that. Up till now, though, you have had to access these things in a tool, such as the X tool, Xprobe 2 tool, or InMap, or queso, or whatever, or Ring. I don't know if how many people have looked at Ring? Seen Ring? Okay, cool. Some. Now to start with, is why you should not leave me in the middle of this thing. I'm going to show you what I've been doing. This is a program that I've written using my library. Now, right now the library works in C and Java. You're looking at Java because Java is easy to make a GUI in. What you see in the bottom right window is loads of modified versions of the InMap database and the queso database. Very soon, once I look at Xprobe 2 and look at its database, since it's now in a file, they'll be in there too. It's a list of all the operating systems that you find in those databases. And then over here, you find little check boxes for the tests. So far, in Java, I've implemented the Mango packet tests of InMap fame and of queso fame. In C, I've also done the X stuff. Next is going to be the T-sequence test and Ring. So let's see if I can get it to work the first time. All right, now, earlier you were mentioning, somebody here was mentioning the fact that Xprobe 1 used a tree, sent one packet, and then based on a tree that it had in its memory, would send the next packet based on the result of the first packet, and as a result would send in total less packets than InMap would, or I think any other test at the time. And as a result, it could limit the number of packets it sent, reducing its IDS profile, increasing speed, all these kind of things. So what if you could do the same thing with InMap? What if you could run InMap one step at a time and then use the results that you got back? Since InMap runs, InMap alone has the 7 Mango packet tests that you see there and a T-sequence test, which tests initial sequence numbers and a port unreachable UDP test. What if you could use those one at a time? Well, this program right here shows what happens if you do that. If I run the InMap 4 and the queso 2 tests, the source port of 10,000, I hope this is open. I hope this is closed. Now, a lot of the values in the test are based on starting sequence number, and this allows you to play with that. Now, no suitable device found. Damn. So unplugging your network cable cord. I'm not going to belabor. I'm not going to play with this too long. In fact, I'm going to move on now anyways, and I'll come back to that. But that's the kind of thing that you can do. I'll just keep that up since I think it's cool. That's the kind of thing you can do when you're able to access the tests in a systematic way. So hopefully now you should be convinced that you might want to hear the rest of the presentation. And again, if you don't, feel free to leave. especially since I know that some of you who dream in Perl could be very upset with the fact that you're not getting Perl code right now. I understand. I feel your pain. Okay, another thing, the TGZ on the CD is useless. Go to my website. All right, who is this code for? Well, the answer is kind of everybody. If you're a hacker, you want to be able to write a script that says, don't run my exploit on anything except an exploitable box. If you were able to detect that you could sort out Windows 2000, version this, rev this, with this service running, in this version, before you ran your tests, what you'd be able to do is have a mini vulnerability test right before you actually ran your exploit, which means that instead of like running a system where you scan the host, you figure out what operating system is running, you figure out what ports are open, you research what hacks are available, you could just run the hack and it would stop if it wasn't the right operating system. It would just not run. On the other hand, if you're writing a worm, I'm not recommending you write a worm, but if you're writing a worm, you might not want to scan Linux hosts over and over and over and over again like you've all seen in your logs. You might just want to scan Windows 2000 boxes. Well, by including all or a portion of an operating system fingerprinting library in your code, you can do that. White hats. The same reason that a black hat is interested in what operating system is running on your network, you should be interested in what operating system is running on your network. Vulnerabilities are based on operating system and service version. Not all versions are vulnerable. Sometimes it's all of BSD. Sometimes it's just FreeBSD. Sometimes it's just Linux. Sometimes it's just Linux 2.2. You care because you're going to be able to get broken into based on what you're running on your network. Now, on the other hand, besides from a security perspective, it would be nice for administrators to know what's running on their network. So these are just the reasons that you are interested in operating system fingerprinting. Avery's talk is so deep that he just kind of goes into it and he doesn't realize, he doesn't talk to why people are enjoying his code. Most of the people who enjoy his code don't actually do bad things with it, I hope. Okay, this is a deep knowledge track about beta code. If you're here expecting something you can go and then program in your application tomorrow, again, with the Perl people, sorry, not gonna happen. Okay, why a library as opposed to a tool? Well, this way you can write things for yourself that are operating system sensitive. Let's say you don't want to write a hack. Maybe you want your web page to just be displayed for Windows 98. Or maybe you want your web page just to be displayed for Windows, as all of them. Maybe you just want to be able to display one administrative homepage for Windows, one for Linux, one for this. And you want that web page, hopefully I'll be talking about like the Apache module and planning. You want that web page to be able to say, hey, I'm going to give you this content based on what you are. That would be a very, very convenient way to hand out patches. You could hand out exactly the patch that needs to be handed out to exactly the person that needs that patch. It means less clicks, which administrators of thousands of users love. So let's talk about the problems with tools, the problems with programs right now. There's a bunch of tests, right? Some of them are INMAP tests, some of them are queso tests, some of them are XPub tests, some of them are Ring, some of them are service tests. Well, you have different algorithms that are using these things different ways. Algorithm A by Afer and Fidor is now using fuzzy. So it's the most sensitive and advanced algorithm out there. INMAP just uses brute force. It runs all the tests all the time and can come back with pretty good results usually. So you've got some more advanced algorithms. But at the same time, you want to be able to have more control over your algorithm. If you're programming, say, Nessus, you might want to do different things and test differently than you are if you're doing another scanner. If you're doing a web page, for instance, you might want to scan another way. If you're on a friendly network and you're responsible for a network and you're scanning it, you definitely don't want to do tests that are going to possibly hang up any operating systems. There are operating systems, older ones, that will hang up on different versions of INMAP's test. It's just a version of a DOS. You run INMAP on it, and it turns it off. This is a bad thing. So you can have polite, you can have stealthy, things that don't get detected. All these algorithms, though, are meta tests. They're above the test level. They're not actually involved with the tests themselves. They're above the test. And these kinds of algorithms have the problems that Adrian was just talking about when he was saying, how do you deal with the results if you're talking about a load balance test? How do you deal with the results if you're talking about this situation? How do you deal with the results in this situation, this situation? All that's dealing with interpreting the results of a test, which is a meta-level algorithm issue. So what I'm trying to do is provide a way for you to get very easy access to the tests themselves so that you can do whatever you want on top with an algorithm. Okay, why not a library? Well, I'm always going to be playing catch-up. I'm not going to be able to write new tests. I'm not going to be able to write, zippy-doo-dah things. Maybe someday, I'll be able to come up with something new. But in general, people like Aether, Fyodor, these are the people who are going to be writing the new tests. They're going to be coming up with new code. They're going to come up with new algorithms. They're going to be doing the new cool stuff. What's in the library is going to be the yesterday old stuff, but just in a way that you can access. Right, and this is not going to be a tool. I'm never going to hand out something that's going to be particularly useful to you right now. If you're a script kiddie, you're not going to get anything you can run on the command line. Okay, let's talk about a little bit about the background of operating system fingerprinting. The first grandfather of all fingerprintings is queso. How many people have used or heard of queso? How many of you like queso? Okay, less. That's first generation. Why was it first generation? It was the first operating system fingerprinting code, and I'll talk about this a little later, to pull the database outside of the program itself, so that the database of fingerprints and the logic to fingerprint them were separate. After that, we have the passive side, PLF, siphon, stuff that's looking at traffic doing fingerprinting. Right now, I'm not implementing these tests, and these will probably be the last tests that I use, and the reason is that they're not particularly useful for administrators. If you're interested in doing passive fingerprinting, usually you're going to be a person who's interested in not being seen. The other case is when you're interested in seeing what traffic is going in and out of your network. And in that case, I think the fingerprinting, passive fingerprinting stuff that's going to become available with Snort is going to be far better than what I could do real quick. So I'm going to focus on the left side of the map here. So we have InMap. InMap is the seminal operating system fingerprinting. And the reason is it's the first to treat it as a real science. Fyodor used a statistical test. He used mangled packet tests. He used UDP tests. That's a pretty broad spectrum of ways to guess at operating systems to use in tests. And the other thing that he did that's very significant is that he tested lots and lots and lots of operating systems. If you've got OpenBSD running on a little Macintosh like they had last year here, you might be able to get InMap to pick it up. You never know what's going to be in the database, though, and that's a complaint that people like Aether have been pointing out, is that database is so huge that it really is becoming unmanageable and kind of useless, like what he was talking about for the printers. I mean, it's very difficult when you've got 20 signatures, 10 signatures for HP printers, and they all come up. That's just not useful. Okay, second generation is X. X was the first test to use to not send all the packets at once. It made decisions based on previous tests about what test to do next. The problem with that is it was static. That means that the tree was hard-coded. So you had the tests, and then you had the tree, but just like the early versions of fingerprinting software had both tests and algorithm inside the code, the tree and the tests both need to be outside the code. So the algorithm for choosing what test to do when and the tests themselves need to be configurable. So that makes it a second generation. Now, third generation is Xprobe 2, which I didn't know a whole lot about until today. So that code is addressing a lot of the problems with X, which is making it the most advanced fingerprinting system available. Now, once he does all the things that he's planning to do, it will probably be cream of the crop. It will be the tool you want to use because it'll probably incorporate a lot of the tests that InMap is using, the T-sequence test, these kinds of things. Hopefully, what I'll be able to do is look at their API, the one that he was just describing, and use my library to code tests for his API, which means the fact that I finished the queso and InMap tests and made them separate and pulled them out and done all that work will mean that he's kind of handed that on a silver platter, but we haven't talked about it, so that's up in the air. Okay, the other thing is ring. Now, the one unique thing about T-sequence tests in InMap was that it was totally normal traffic. What it did is it sent a packet, SYN packet. How many people understand the TCP handshake? If you don't understand the TCP handshake, what I'm going to say right now is going to be just like gobbledygook, right? So just forget it if you don't understand that. You send a SYN packet with a sequence number. It's going to respond back with a SYNAC with a certain value in its packet that corresponds in some way to the value that you sent. Now, by doing that over and over and over again, you can get a statistical relationship between what you send and what you get back. So you can find out if they're generating these sequence numbers, the ones that come in response randomly, or they're adding something to your sequence number. Very common is to add 100 bytes or add the value of 800 or some other constant. But there's no way to detect that. That will slip through a firewall as long as you've got a website running. That's it. All on the firewall, you'll be able to get that test through. So the T-sequence test is unique because it's extremely stealthy. It uses normal traffic. It's not doing anything illegal at all. If you stop T-sequence test, you stop your web server. That's the only way to stop that test. It's normal TCP traffic. Now the other thing that's normal TCP traffic is ring. And the way ring works is that when you send out a SYN packet and then they send back a response and then you do nothing, they're going to try to repair that connection. Like it's supposed to be you talk, I talk, you talk, I talk, okay, we're talking, that kind of thing. Well, instead I go, I talk, and they go, we talk, and then you go, and then you say, they're going to say, we talk, we talk, we talk, and the periods between the we talks is something that's constant per TCP/IP stack implementation, which means you can test for it, which means you can determine which operating system is running. Now, what's the significant thing about that? It's very much like FIDO or InMap's T-sequence test in that it uses totally normal traffic. It's not something you can detect with an IDS system. It's the same from an IDS perspective as someone unplugging their Ethernet cord or a host going down. The number of false positives you get by writing an IDS signature for that kind of a test would be phenomenal. So both the T-sequence test and the ring test represent methods for getting an operating system in a very stealthy way. We're talking about queso again. If you want to know about queso, read Fidor's paper. In fact, if you want to know about operating system fingerprinting, read Fidor, InMap Fidor's paper. That's the seminal work in the field. It's the first real scientific look at it. Now, if you really want to know about operating system, then read Aver's X paper. It's that thick, and you'll know a lot more. But if you want to start out, if you want to review these concepts, Fidor's paper is a great place to start. InMap, exactly what I just said. Robust database, really big, and it's the first to be really scientific and really systematic about the way you fingerprint. X. First, use intelligence. It's all SciMP, but it's got a hard-coded algorithm for determining what tree it is. Ring, we just talked about it. X2, you know as much as me. All the stuff that you just said, that's what X2 is. Can everybody hear me still? Cool. Okay, let's talk about the structure of my library. All the tests right now are actually written in C. Now, the reason that that's the case is that C has the best and most documented method for accessing raw IP sockets. Most of the tests, many of the tests involve writing packets in very specific and non-usual ways. So you need to have access to that those raw libraries. The other thing is that I use LibNet, the beta version, because it's cool and does things for me that I don't have to sort things out because I use it. It's got a lot of functionality. It's really cool. So that's in C too. The other thing is that actually running the tests is irrelevant. The important thing is you have that information from somewhere. So the easiest way to write the test in C, so that's how I did. Okay, C applications, Java applications, C++, Perl applications across the top there. And then beneath those, you have the C library, Java library, C++ library, and Perl library. The Java library is the one that's the most robust, obviously, because that's the one that I just showed you. So right now I'm going for implementing X, queso, nmap, and ring, and all these different tests, and having them move up in between these different programming languages. So wouldn't it be cool if you could write a Perl script that says, if Windows, do this, or if some function returns as Windows, do this, or if some function returns as Windows 2000, you do this. This would be a good thing. The other thing with Perl, and this is something that actually I'd love to get this functionality from Perl into other languages once I get done, is you can take a look at Rainforest Puppy's libwhisker. Libwhisker is capable of doing very, very accurate fingerprinting of the web port. It can sort out what web server is running on a particular computer. I was doing a pen test recently, and they were using a FreeBSD. It was a product that was based on FreeBSD, and they were using it to proxy an MT2000 web server. Well, when Whisker first went into it, it said, oh, it's reporting back, it's saying it's Windows 2000. So that's what it is initially, and then it runs a bunch of other tests and finds that the actual behavior of the server is more like FreeBSD. So it comes back and says, actually, no, this is Apache. This is Apache. It looked like Windows 2000 at the beginning, but it's really Apache. Wouldn't it be neat if you could get this is what the web server really is from libwhisker, and move it over and make decisions based on that in other programming languages. So you could say, because Apache, for instance, runs on Windows 2000. Rarely do people do that, but it does, it runs. So you can get that legitimate header back from that web server. And then if you're running IIS hacks against that box, why? So being able to say, for instance, run a T-sequence test against port 80, get a sequence number, run a ring test against port 80, those are both totally stealthy, and then just ask for do a service test to find out what web server is running, you'd be able to fingerprint a host with absolutely no IDS detectable stuff. All that stuff is totally legitimate traffic, and it would tell you a lot of information. So every language here has different advantages. The reason I did Java first is because most of what I want to focus on is how OOP, and object-oriented programming, really affects the fingerprinting science. And Java is it's very easy to get threads and OOP out of Java. So I started there, and then I'll use what I've learned there to do the other ones. So everyone kind of understand what I'm talking about here? Have I lost everyone? Have I not lost everyone? Okay. Okay, right now, for my .c files, each test is written as a listen function and as a send function. Now, for instance, the sending portion of nmap T1 through T7 are very different, but the fingerprinting portion are all identical, so you can collapse the listening file into one. So basically, from a C perspective, it's functional programming. By using my C library, you should be able to just call functions with the right stuff and run whatever test you want. Let's take a look at the C code. Talk amongst yourselves. Seeing in a moment, all of my code is released in GNU. So you can use it to load. Testing. Okay, it's back on. You have a Can you hear me now? So you have a function call takes a source IP, destination IP, source port, destination port, and an initial sequence number. Now, in C++ or Java, what you can do is overload these functions so that you don't actually have to give it a sequence number. You don't even have to give it a source port number. Basically, the source port, in the in-map meta-level algorithm, is chosen for you. It's chosen randomly. But you don't have to do it that way. If you want to, you can configure just about everything. On the other hand, the overloaded functions will allow you to run it the same way that in-map does. So if you just want to have a destination IP, assuming that you're using your own IP, so you don't need a source IP, assuming that you're going to generate a source port randomly, so you don't need a source port, and you need a destination port, you don't need a sequence number because it's going to choose that randomly, then that function will just have destination port, destination IP. You build the options in that TCP tests. Use crazy options. It's one of the IDS signatures of the tests. Anytime you see this particular set of options all together in one place in a packet, it's usually an in-map test. Then you set up the build TCP portion of it. I don't know how many of you are familiar with libnet. And you use the SYN port and the bogus port here. There are so many flags that a TCP packet can have. There is one that is not defined. That's a bogus. In-map sets that flag. Most TCP IP implementations have no idea what to do with it. So they'll respond back. Sometimes an operating system will take the packet that it's reading in, change it into the response, which means they don't actually write a new packet. If they do that, then the bogus flag in the packet that comes back will also be set. So depending on how you implement it, the results are different. You make enough space in the IP and then you send the test. All right, moving back to my PowerPoint, talk amongst yourselves. Okay, here is something that I would actually like some feedback from people at this conference about. And the question is, how do you classify an operating system? For instance, the way I'm doing it right now is with OS family name, major version, minor version, other information, and architecture. I know for a fact that this is not a good way to do it. And the reason is think about how many BSD variants there are. If you have a family and you want to be able to write a test that's for all BSD, or you want to be able to write an exploit that's for all BSD boxes, if you're doing that, you want to say if the family name, if this top level group is BSD, then run the test. If not, then don't run the test or the exploit. Okay, if you do that, then what goes in major versions, since that's the next steps down, would be FreeBSD. And then under that would be 4 point something. Well, the problem is it just doesn't split up very well. Like for instance, Windows. Windows is the family name, then you have 98 and all these other things. So when you're using Windows and the major version is 98, that's comparable to the entire operating system of FreeBSD? Probably shouldn't be. So how do you classify an operating system? How do you group them? That's a difficult question, and it really takes some knowledge of operating system history, of which I unfortunately know only the latter part. So I'd like some discussion, perhaps. If you'd like to come talk to me about this afterwards, please do. But every class JLS test, which every test is a subclass of, has this information in it. Not only that, it has again, if you don't know Java, then this is going to sound irrelevant to you, so just ignore it. I've redone the equivalency stuff so that it does the equivalency in such a way that it will order any given set of these operating systems by their actual classifications. So it'll take OS family name into account first, then major version, then minor version, then something like this, so that you can use the actual Java comparative function, and it'll actually return a negative or positive number based on the relationship between two operating systems, which means you can for a given operating system, you can run tests based on less or more stuff. If you know Java, then perhaps you know what I mean. If not, perhaps you know what I mean. Okay. Okay, threading. Operating system fingerprinting should be threaded. And the reason is that there are some tests that are related to each other. For instance, that tree that X did. But there are other tests that are totally irrelevant. So you could be running the X tree, all those ICMP tests, at the same time you're running in-map tests, at the same time you're running service tests, and then the whole time you could be using, race condition safe data objects to move information about what tests should be run. So you can have, basically what this allows you to do is write testing algorithms that will turn on its head based on the results of one test. It means that you can write dynamic trees. So you can say, well, let's start running these 4 tests, and then get those 4 tests back, and as a result run total different other set of tests. Now the reason that's important is that one of the problems with in-maps fingerprinting and just vulnerability assessment in general is that it tends to be slow. It takes a long time to do this. If you can do stuff in parallel, if you can get information in different directions at the same time, that gives you a huge advantage. Okay, you've already looked at the code. Let's see. Perl module and C++ module will happen someday. If you're a Perl guy and you love writing modules that access C libraries and move like large amounts of data back and forth, please come talk to me. I'd love to have your help. C++ I think I'll be able to handle just because it's easy. Okay, what's the future of my fingerprinting library? Well, obviously, it's to implement all the tests. Like when you're able to access all the tests in my library in one place, even if that's all I give you, that means that it's an easy place for you to start, assuming you want to write operating system fingerprinting code. The other thing is service fingerprinting. There's a program called WinFingerprint that does nothing but fingerprint all of those dangerous, turn them off please, 130x Windows ports that you should never be using, ever. So you can run an entire sequence of service testing to fingerprint what NetBIOS, what SMB, all those things, what they're doing, what they mean. The stuff that it can return, I haven't looked at the code carefully. It looks like it's pretty impressive, very much like LibWhisker's HTTP ability. And as a result, if you can get that service information, then what you can do is you can have associations between service generations, like SendMail version this goes with Solaris version this, and IIS version this goes with Windows version this. Like some of these things you happen to know off the top of your head. Some of them, on the other hand, are a little more complicated. But since vulnerabilities are based on service number and operating system number, it would be nice to be able to use service to get operating system number guesses and use operating system guesses to get service number guesses. So hopefully we'll be developing a database about what services go with what operating systems. I'm sure somebody's done that, so it wouldn't be hard. The other thing is that what you can get if you have all this stuff is a CVE database, kind of a Nessus Lite. Nessus actually tests to figure out whether or not you're vulnerable. What if you don't care? What if you don't really care if you're vulnerable or not? What if you're running a version of Windows blah 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 or FreeBSD blah 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 that's vulnerable to 5 things? Well, maybe all you cared about is that you need to upgrade to the next version. Maybe you're on FreeBSD 4.0 and you need to be on 4.1. Maybe you're on Windows 2000 and you really should be on Windows XP. If that's all you care about and you're an administrator, you don't need to have a full-blown vulnerability test to make sure you are in fact vulnerable to something. All you need to know is not current version, please patch. That's it. So if you can be very aware of operating system fingerprints and service fingerprints, you get a very, very cheap, very, very fast vulnerability scanner. The other thing is to develop a simple scanner. Something that does, I don't know, a quarter of what InMap does. I don't know if you guys have looked at InMap 3. It's up on insecure.org. You definitely ought to go take a look. The Windows versions of InMap and the Unix versions are merged. It's pretty cool. But I definitely don't want to write stuff that competes with these tools that are out there because they're so good that it's very unlikely that I'll ever be able to generate something that's going to be able to keep pace with those technological developments. Rather, I prefer to kind of imitate what they did last week. I think the coolest thing would be a LibOS Apache module so that you could give different information to different users based on their operating system. So you set your proxy up so that, let's say, you combine your CD database scanner and your LibOS Apache model, you scan your network, you come up with 192.168.1.5 is a vulnerable version of FreeBSD. You put the patch up on a web server, and you say, if FreeBSD version this, show this page. And then you write into your proxy for your web surfing that they have to go to the patch version update page first. Well, that means that you scan your network for all the vulnerable things, you put the patches that they need up on the website, and then those servers or workstations that are vulnerable will automatically be forced to go download the patches before they can go continue surfing. Now, they might not install the patches, but at least they download it, and that's a start. You cannot lead, you cannot make a horse drink. Okay, that's everything. Thank you, and do you have any questions? Yes, and actually I'm going to have to do microphone switching since nobody can hear, so if you'll just come up. Oh, I'm sorry. That's a very good question. And it's on the HTML documentation that's inside the CD. It's www.synseer.net. SYNSEER. Good point. Next question. Next question. Can't hear a word you're saying. That would be a good idea. Yes. But you asked TCL, and I said yes. Anybody else? Okay, I officially am relinquishing the microphone. Please feel free to come up and do the one-on-one questions if you feel like it. Bye-bye now.